Howdy, folks, and welcome back to another episode of the Storm Chaser Coaching Podcast. I'm your host, Gabriel Harber, and I'm joined today by Coach Kyle Gillett. Kyle, how you doing, man?
I'm doing fantastic, Gabe. Thank you so much for having me. I can't wait to talk a little bit more about modeling.
Hold on there a second. I know you're pretty and everything, but I don't know if I agreed to a modeling contract.
We're talking about the storm chasing community here, right? So we've got a lot of use for models. And it's funny, I always, when I go to the College of DuPage website, shorthand, I just type COD models. And sometimes I do worry about what will come up, but usually the College of DuPage website is the first one that pops up. And yeah, numerical weather prediction. Let me put it that way. Hopefully that's
Yeah,
better.
numerical weather prediction. And by the way, I'm very impressed that you're willing to play Google Roulette like that. You do never know what those search results are going to bear.
Yeah, you never know. Yep.
So, Kyle, of course, you created the numerical weather models module that people have undoubtedly heard about on one of our social media channels or on Twitter or whatnot. It's a really awesome course, and I can't wait for people to check it out. It's in the Chaser Academy, which is, of course, our subscription based product. And if people want to go into the Chaser Academy, check it out, look around, and then decide they want to sign up, they can use promo code podcast and you'll get 20% off of your first month. So really good deal over there. And Kyle, I was thinking about it. Trey did the radar for storm chasing last month. That's the standard issue weapon that you have to have with you when you're out in the field chasing. But I feel like the numerical weather models are a very close second because that's really your go-to asset when you are developing a forecast in the days leading up to a chase. So they really go hand in hand as the I don't even think you could decide which one is number one and which one is number two in terms of the foundation for anybody who wants to learn how to forecast and chase storms.
Definitely. And a lot of your radar interpretation is, and I'm sure Trey has discussed this so many times, right? It's what you're seeing on the radar, what you're seeing with your eyes, right? But it's also having this in the back of your head intuition for how the day is supposed to evolve. And of course, that comes from you making your forecast. And that's inevitably going to include forecast models as well. So it's really just all intertwined together. And having all these tools and all these tips and tricks and things, it's going to help you make the best decisions before the chase and during the chase.
Absolutely. And while people can get a full crash course on numerical weather models in the Chaser Academy, for these podcast episodes, we select a few really spicy tips that can help people improve their forecasting and storm chasing right away. So, without further ado, let's dive into those. The first one, of course, being Updraft Helicity tracks.
Mhm.
And if you haven't been around the block on social media, you've missed out because I think some of the most egregious examples of hype casting that I have ever seen have come as a result of the Updraft Helicity tracks. Kyle, what is it that makes these so difficult to interpret and apply correctly?
There's a lot that goes into that, and you can find them on most of your what we call convective allowing models, which means that they're able to resolve convection and they're really small. Grid spacing, which means we can actually see the convection to an extent. And so, what it's attempting to do in a very high level sense is it's trying to indicate where we might have mid level rotation. So, the very basic way to understand this is it's trying to identify areas of mesocyclonic rotation, the mesocyclonic spin, and that's what helicity is. It's some spin in the atmosphere. And so generally in model output, what you're going to see is this kind of 2 to 5 kilometer updraft helicity track. You might see it for it could be 1 to 3 hour accumulated. It could be the total run accumulated, right? We see these maps thrown all over the place. What actually are they? They're like I said, an attempt to identify those kind of mid-level mesocyclone features. But there's a lot of nuance that goes into that, right? So imagine in your head, you see this her run of some event. Maybe we're a couple days out from a severe weather event down south in Dixie, and a lot of people are talking, oh my gosh, outbreak, right? And there might be huge, like updraft helicity swaths going across Mississippi or Alabama or something. I know you could see that picture in your head, right? So what that actually
Yep.
is showing is the potential for there to be a updraft that has some spin, and associated with that spin is going to be upward motion. And generally, what on most model sites is greater than 75 meters per second of spin, more or less. So, in a rough sense, if you're looking at that map, what you could interpret that as is if you see a storm that has this updraft helicity track, you could assume that it is rotating. Now, that's an okay assumption to make. But what a lot of people will inevitably translate that to is tornado potential. Of course, you would imagine, right? Rotation, tornado potential, they are hand in hand, but not every rotating supercell thunderstorm is going to be producing a tornado. And one thing to keep in mind is that on those maps, they're 2 to 5 kilometers, right? So that is getting up into the kind of middle levels of the atmosphere, in a sense, maybe the lower half of the mid levels of the atmosphere. When we're talking tornadoes, we're talking the lowest maybe 500 meters, the lowest 1 kilometer maximum. And so this updraft helicity track map, this is showing you updraft helicity tracks above that layer. The number one takeaway from this kind of updraft helicity track thing is that it's not tornadoes and it's not low level rotation, right? It's not spin at the lowest level for most of these model sites that you'll see. It is essentially strong rotating updrafts or the mesocyclones, but in the middle levels. So one thing that I see a lot, if you have a warm frontal boundary, right, you can have supercells on both sides of the boundary. You can have a supercell that forms on the warm side and then crosses over to the cold side. Of course, we know when it's on the cold side of the warm front, it's no longer surface based. Now, that doesn't mean that it won't have a mesocyclone above the surface, right? So you might still see updraft helicity tracks north of the warm front. It doesn't necessarily mean that it's a tornado producing storm, right? It's just an indication that there's a mid-level mesocyclone. So I see that often. There's a lot of sharing of this updraft helicity track map, and that's fine, right? That's what it's for. But we have to have that good understanding to really be able to use this tool. And so again, at the end of the day, all it's trying to show you is that this storm could be a rotating supercell with a mid-level mesocyclone. It's not necessarily hinting at what could be going on in the lower levels of the storm.
Excellent advice, and hopefully that tempers a lot of people from hyping it up when they see those mass
Mhm.
swaths of red and yellow and green and everything in between.
Right.
Not to continue picking on the hype casters, but I feel like we have to here with your second tip, which is figuring out the correct way to, we'll say, pluck, for lack of a better
Mhm.
term, soundings on a model website. So first of all, if you could actually just explain to people what does it mean to pluck or generate a sounding in a numerical model, and why is there a correct or an incorrect way to do it?
Definitely. And I'll start by saying this for the hypecaster idea, right? You're going to miss out on a lot of good storm chases, or you're going to have a lot of busts if we're not using those kind of first principle ideas when it comes to forecasting. I definitely don't want to pick, right? But at the same time, you want to be able to just share these ideas that will help wrangle in some of those thoughts and ideas when you're going through your forecast. So that's why we're talking about these things, right? So the next one here is plucking soundings. I think I've always used Pluck to explain this, but imagine you're on the College of DuPage website or the Pivotal Weather or something, one of your favorite websites that you can get soundings from. And you're like scrolling through, maybe you have temperature or dew point or reflectivity or something, right? You're scrolling through and then you click that map and you pull up a sounding, right? So imagine that you have that map in front of you and you have to pick a location on that map to pluck out a sounding. Now, you've probably heard this before, right? You forecast with knowledge of meteorology, you don't forecast with simulated reflectivity. And that is true. However, when you are plucking soundings from a model site, I recommend that you do actually use the reflectivity here. This is the one true time when you shouldn't be straying away from using reflectivity. And I'll explain why. We just talked about the updraft helicity track, right? What that is showing us is an area of essentially violent rotation and violent upward motion in the middle of a thunderstorm. So if you have this reflectivity map in front of you and you start plucking these soundings right next to those updraft helicity tracks or right in that reflectivity core of whatever simulated storms there are, what you're going to end up having is contamination from the violent motion associated with that thunderstorm in the environment right around it. And so the sounding that you see popping up on your screen is not actually representative of the environment that the storm is going to feel. So it's important to understand that. Think about it in two boxes in your head, right? We like to put everything in boxes. The first box is the environment without a storm. The second is the environment with a storm. the environment with the storm is going to have some modification to it, right? You can't just have a storm moving through the atmosphere without disturbing it or perturbing it or something, right? So if you are on some reflectivity map and you pluck a sounding from in the middle of a storm, what you're actually seeing is the environment inside the storm. And even to take that a step further, it's not even a real storm, it's a numerically simulated storm. So there's a lot of funky things that can happen near those storms on the reflectivity map in a model. So the right way to pluck a sounding to get in that first box of the environment without a storm is to go generally to the east and to the south. Picture in your head, maybe we're looking at the Texas Panhandle. Okay, so zoom in on that area of the Texas Panhandle. Maybe there's storms coming down from the northwest, right? What you might want to do is go into that kind of southeast corner of the Texas Panhandle and take a sounding from there, because that is an undisturbed atmosphere. And that is the atmosphere that's going to be actually feeding these thunderstorms within the next 30 minutes or 60 minutes or whatever. That's the environment you want to forecast on. So what a lot of times you'll see, and if you can visualize this in your head, we also, of course, talk about this in the actual training module, but if you can imagine in your head a sounding that has all those kind of orange or red bars that kind of stream all the way across where the temperature and dew point profile are, those are indications of upward motion. And when they go all the way across from the left all the way to the right, that means you have plucked your sounding from the middle of a storm updraft. And whatever that sounding says should be completely ignored because it's just not real and it's not useful for you in your forecast. That said, if you pluck a sounding too close to, let's say we have a supercell on the HER, you can clearly see that it's probably a supercell. It's got an updraft helicity track. If you take that sounding too close to that, you're actually going to get a modification of the environment by the supercell. That could make the environment look quote unquote too good, right? You could have big, crazy shear, and maybe you've got a lot of moisture because you're real close to the storm. So the cape is big, a lot of 0 to 3 kilometer cape in there. But that's actually because of the storm, what it's doing to the environment, not what the environment is doing to the storm. And that's what we want to see in forecasting is what is the environment going to do to the storm. So that's why we want to be careful when we pluck those soundings out, because where you take the sounding from is going to matter for your ability to interpret what it actually means relative to some area of convection.
Very interesting, the dynamics at play with needing to actually blend together two separate parameters, the simulated reflectivity, and then actually, or I don't know if even parameters is the right term, but two separate products within the
Mm-hmm.
numerical weather models. And I think that is a theme that comes up a lot when you are talking about the numerical weather models in your training module.
Absolutely. And again, like we're trying to provide tricks and things like that, but also things that I see all the time that I'm like, oh man, little things that we could tweak to help you better be able to go through your forecast process. And one of those big ones is how to pluck sounding. So I actually have several minutes I go through on an example, and I'm actually clicking soundings around, showing how they're different and things like that. I think it's massively important to be able to understand where do you get those soundings from relative to where your storms are, because it's going to have a big impact as to what you're able to analyze. And of course, whatever you're analyzing, you're going to make a decision based on whatever you looked at, and then your decision is going to become your chase, right? So you don't want to be making bad chase decisions because you had a bad analysis because you were looking at bad data, right? So we're just trying to put our ducks in a row, if you will. And one of the big things is being able to pluck soundings in the right spot.
I really like the way you put that, that you have to make good decisions when you're forecasting and using these numerical weather models because your decisions become your chase. I almost feel like
Absolutely.
that's a little maxim that we could just all commit to memory to keep in our
Mm.
heads when we actually start to make our forecast. It's almost like a bumper sticker. Hell, I might even have
Yeah,
to license that off you for some merch for Storm
let's
Chaser
do it.
coaching.
Yeah, that's cool.
Your forecast decisions become your chase. Forecast wisely.
It
Something like
really
that.
does. It really does. Like I said at the beginning of this, going back to Trey's module on radar, right? When you're analyzing radar, at least when I'm analyzing radar, I might see some storm behavior, but then I can tap into what I had for a forecast and say, okay, here's what the storm's doing now. This makes sense because of the environment. Here's how I think it might evolve, right? So you're always making these little mini forecasts, these little mini decisions So if we can start from step one with the right information, then all the decisions that cascade out of that are just going to be better.
Not to inject my own personal experience too much into this podcast, because this is all about the module that you created, but fans of my other show, Chaser Chat, are going to know that I love to go off on these little tangents occasionally and compare one thing to another. And one thing it really reminds me of as you're talking about this is, of all things, actually, Magic the Gathering. And I hear all of you rolling your eyes and saying nerd collectively. That's perfectly fine. But I actually grew up playing a little Magic the Gathering competitively. And one of the things that you were always looking for when you were building a deck in whatever format you were playing is these little synergies between cards. Of course, you wanted to have an overall strategy that your deck was trying to accomplish, a game plan, so to speak. But you also wanted to have these little pockets of individual synergy that if 2 or 3 components came together, they would form something extremely powerful. And so I like the way you described that. And that's how I relate it when you were talking about how even when you're out chasing with your larger plan in mind, you're always making these little mini forecasts in your head between these 2 ingredients or this thing and that thing. That makes a lot of sense to me and tracks with experience I've had in other strategically based endeavors.
Yeah, definitely. And it's so important. You can't go out there expecting it to evolve exactly how you forecasted it to. Little things are going to change, and the storm ended up firing 50 miles south of where it was, or oh, gosh, it seems cooler out now than it was supposed to be, right? So we always have to be altering our decisions. But if you've got a solid forecast to help guide those decisions beforehand, it's going to totally change the game.
All right, Kyle, we are on to our third and final tip for this podcast. And it's sad to say, but our apparently coaches are no fans of the NAM 3 kilometer because Trey has nothing good to say about it ever, and you are going to pick on it here. Specifically, you said the over-convecting issue. So what do you got for us?
Model biases are important, right? Real quick background on what a model is. It's just us taking what the atmosphere currently is, throwing it through a bunch of equations and trying to simulate what might happen in the future, right? So it really is just a bunch of math and computing at its core. So what that means is, number one, no model is the actual atmosphere. But what it also means is that sometimes the way that we handle the equations or other things can have an effect, can have a weight on how the model handles certain features. And I'm with Trey on this. With the NAM 3 kilometers, I'll put it this way: one of the best examples of how things can go wrong in a model. I don't know if maybe that helps. I called it the best, but the best at being bad. I'll put it that way. There's a lot wrong with the NAM in general between some of the biases that it has, but then the NAM 3 kilometer. So the actual NAM model, 12 kilometers off the top of my head, I think I have that right. And then the NAM 3 kilometers, a 3 kilometer model. So the resolution or the number of grid points, the finer the scale, you get a better scale as you go down to 3 kilometer NAM. However, there are a ton of issues with biases. So essentially what the bias is that in general, you might have a situation where the actual temperature is always 5 degrees warmer than what the NAM 3 kilometer says. That is a cold bias by the NAM 3 kilometer. So with that little bit of background, I'll explain this one. You've probably seen this multiple times when you're forecasting storms with models. So it is the over-convecting issue and the ability for the NAM 3 kilometer to turn every storm into a linear squally kind of MCS crap fest thing here. So what happens is that, first of all, the NAM is cold and moist, and in general, usually it's too cold and it has too much moisture, particularly in the lower parts of the atmosphere. Because of that, it has some microphysics issues, which at the end of the day, without getting too in the weeds here, it causes cold pools to be too strong. Now, a cold pool is essentially that region of cool air that is sitting underneath of a thunderstorm due to its downdraft. So if you've ever had a kind of a storm that gusts out at you, like an outflow dominant storm, that's the storm's cold pool rushing out away. A supercell that is inflow dominant without the cold pool rushing out at you, that means its cold pool is tucked away nicely, and it's going to continue to move on as a discrete storm, all else held equal, and it's just going to do its thing. Now, if your cold pool is too strong, that means it's going to gust out and rush away. When that happens in real life, physically, you're going to end up with storms that become more upscale. They grow upscale, they become more linear, they become more of that squally look, messy, right? So the NAM has a bias to overpredict the strength of cold pools. What that leads to, if you're imagining a simulated reflectivity in your head right now, that means that you might have a couple of storms that start by themselves initially, and within the next hour or the hour after that, it's suddenly into a gigantic squall line because it causes storms to be too linear with too much upscale growth of that convection after it develops. There's a lot of kind of reasons why that's the case. I do go into this quite a bit more, other biases for other models and things in the actual training, but this is a big one that I see all the time. And a lot of people say, oh gosh, the NAM this, the NAM that, right? Just like how to pluck soundings or some of these other tips and tricks, you got to know how to use the certain tools for the job. And in this case, and I'm sure that Trey would agree with this, I almost never use the NAM for anything. And that goes for the NAM and the 3 kilometer NAM. I just don't like how it handles convection, right? And a bias is not just something that it happens and then the rest of the model is fine, right? The atmosphere is a fluid, and it's also a fluid inside of these models. So if there's one thing wrong, like too much cold pool, that is going to trigger other things to happen in the model that are going to end up being wrong. So for me, I can't trust the NAM with almost anything, right? It doesn't mean necessarily the HER is much better. It has its own biases and whatnot. We get into that in the module, but over predicting the cold pool strength is a massive issue in the 3 kilometer NAM. And that's why if you ever look at the NAM, it's just always like a squally MCS kind of mess looking garbage. And then you look at the HER and it has 3 isolated supercells or something like that.
So hard to find good models these days, though. The NAM 3 kilometer, the HER. Where are all the good models at, Kyle? Where'd they go to?
You know what? There's a lot of work being done on a new kind of overall system of models. There's a lot of work being done in the research community right now. So as time goes on, we're only going to learn more and become better. And I hope that within the next 5 to 10 years, we have a new suite of models. And this is roughly the plan that are going to be able to fix these biases. It's important in a sense that some models have biases because then we can better understand what math has to be fixed to compensate for that. And
Hmm.
as much as it sucks because we have operational tools that kind of, for lack of a better word, suck, it's still nice that we have this to grow and become better. Soon, we will eventually see the fruits of having to deal with this model forever and ever so far.
And the best part about all of this is that if you are a Storm Chaser coaching member, you are going to be able to access Kyle's updated numerical weather models module when it comes out in 5 to 10 years. We're
Absolutely.
projected a little far out into the future with that one. If what you say is true and we're going to have an entirely new suite of models, that's probably going to necessitate a little update to the previous training module.
Oh, absolutely. Yeah, I don't talk about it too much in the module, the new system. I don't really touch on it much at all. But if you want to research any of that yourself, right now the plan is for it to be called the UFS, which is the Unified Forecast System. And from that, there's going to be like a GFS, HER, the AHFs, the HAF,
They
which is
all
the
have the
Hurricane
most like
Forecast Model.
esoteric little
Yeah,
abbreviations for their names and stuff.
it's alphabet soup,
So,
right? So
yeah.
yeah, UFS, and it's just going to be different versions of the models that we have now, but all uniformed together. They're working on it, and as far as I know, it should be here soon.
Awesome. Kyle, really appreciate you taking the time to give us these 3 tips for using numerical weather models here today. And all of you who are listening, if you thought all of that sounded cool, you're definitely going to love the training module on weather models over at stormchasercoaching.com. If you head over there and you sign up for the Chaser Academy, use promo code podcast. That's going to get you 20% off your first month, and you will instantly have access to that training module and everything else that we have in the Chaser Academy. There is Chase and Explain content. We have monthly members only Q&A sessions. And then, like I mentioned, lots of these in-depth training modules for you to sink your teeth into and develop a deeper understanding of forecasting and storm chasing. So Kyle, again, thank you so much for joining me. And we will be back again soon with another episode, folks.
Thanks for having me.